Good afternoon, good morning to the IMA webinar 3D metal printing opportunities for magnesium. The IMA, the International Magnesium Association, welcomes you warmly to another, hopefully for you, interesting webinar. We have lined up a very comprehensive and interesting range of speakers. Before I would like to introduce myself, I'm Martin Tauber. I'm the European representative of the International Magnesium Association. And as most of you know, the International Magnesium Association is a global network which represents most of the value chain active in magnesium. That starts from primary producers down to tier ones, tier twos companies, OEMs, but also equipment manufacturers, university and institutes as well. Today the topic is 3D metal printing, not a very let's say a mature field for magnesium. For the webinar, some housekeeping rules for you as well. You as a listener of the webinar, your microphone is muted, so you can interact with all the speakers during their sessions and in the Q&As via the Q&A function. The webinar is recorded and will be made available to the participants via a link by email afterwards. For those questions we are not able to answer, we'll try to answer these questions by email later. We'll have 4 speakers today. We have 3 member companies of IMA speaking. That's Luxfer, that's the Helmholtz Institute, and Georg Fischer Casting Solutions, and a guest speaker from LKR in Ranshofen. Each speaker will have 20 minutes, and then we'll have a small Q&A sessions. It's up to the speaker who wants to answer questions during the session, so it's completely, I will leave it up to him. Some introduction to additional additive manufacturing or 3D printing. That's out of a study done with one of our media partners, Spotlight Metal. I think they have approached like 600 companies, and that's just for us to warm up to see where additive manufacturing stands in the industry. So if you see the slide on the left side, there is a high number of almost 60% is saying that they use 3D printing from time to time. 13% have not done it and not planned it either, and 13% are within the next 5 years. So I think that's for all metals. That's for metals and polymers as well. In the other chart on the right side, you see where the additive manufacturing is going to, mainly for prototypes, new components, products, tools, spare parts. So it's obviously a technology change for every company, but it's certainly in the picture for the next 5 years. So with that, I want to start with our first speaker. Our first speaker is Dr. Rajiv Tandon. He's Director of Technology at Luxfer, and he has 20 years of business and metallurgical experience in the ferrous and non-ferrous powder-based manufacturing processes and application. So please, the floor is yours.
Thank you, Martin. Can you see my screen?
Yes.
Okay, Martin, can you see this?
Yes.
All right. So,
Yes, it's working.
so hello everyone, and thank you for joining this webinar. As Martin said, my name is Rajiv Tandon, and in my presentation, I'm going to be talking about an overview of magnesium additive manufacturing, and I'm going to be addressing this from a powders perspective, and hopefully give you a good background in terms of what the efforts have been so far in this field, which has only been active for about 10 or 11 years now, as I've kept track of it, and it'll be my objective to give you a status of what is the work that has been done, or some of the key work that has been done while keeping the powders perspective in mind. The agenda for my talk is as follows. I have a very brief introduction to the company, as some of the participants may be aware of Luxfer's activity as a part of the International Magnesium Association, but some may not. I will also then focus a slide on what I consider to be a timeline of key magnesium additive developments. And then I will go on to discuss briefly what kind of powders we manufacture and how the powders could play a critical role in magnesium additive manufacturing. And after that, I have a couple of examples of the work that we have done with the magnesium laser powderbed fusion and directed energy deposition, which I would like to present mainly to highlight some of the promising potential with respect to the mechanical properties that have been achieved. And then I will conclude with a summary slide. So with that, I would like to give you a brief background on Luxfer. So Luxfer Holdings is listed on the New York Stock Exchange under the symbol LXFR. And it operates as two divisions. One is the gas cylinders segment, and the second one is the electron segment. The Luxfer MagTech powders, which is a business unit that I represent, is a part of Luxfer MagTech. We used to be formerly known as magnesium electron powders, and we are basically a group of 4 companies, all specifically in magnesium powder development areas. Some of the attendees in this call are probably very well aware of Luxfer and through Magnesium Electron. They are represented now under the Luxfer Melt Technologies group, and they've been associated in magnesium for a number of years you may be familiar with. So this is just to give you a perspective of how the powders group fits within the overall Luxfer Holdings umbrella. On the powder side, we have 4 powder plants, all on the East Coast. We have 1 plant up in Canada, but for the purposes of this discussion, which is focused on magnesium additive manufacturing, the 2 core plants that deal with the powder production in this area are located in Pennsylvania. We have 2 large-scale production atomizers, which atomize magnesium using inert gas, and we have a plant in New Jersey where I'm located, where basically we do other kinds of magnesium products, but for mainly for specialty alloys that we tend to refer to, which is magnesium alloy powders. They are being produced in 2 of our Pennsylvania plants. So I'll give you a brief background to the timeline that this industry has seen specific to magnesium. The effort basically for us started back in 2012 timeframe when we installed small scale production atomizer, and the objective was to be able to produce magnesium alloy powders. And at that time, the focus was not primarily additive, but it was developing capabilities in lightweight alloys, which was focused on lightweight structural application vis-a-vis traditional powder metallurgy methods. And then over the years, we have successfully produced and actually evaluated a variety of powders that range from the rare earth containing powders such as WE43, EB31A, AZ91, and then more recently AZ31, Z41, along with a whole bunch of custom alloys. So as far as magnesium additive goes, the earliest work that can be traced back was in the 2009 timeframe, which came out of Hong Kong Polytechnic Institute, and it focused on pure magnesium. And as you would expect, most of these work with magnesium, realizing the challenges of working with magnesium were basically based out of a lab using glove box, inert gas. And this group specifically was working on developing basic parameters for biomedical scaffold, which seems to be one of the areas which has driven a lot of magnesium work, given magnesium's propensity to be, to be considered as an implantable material. So that work basically focused mostly, as I said, on developing parameters and simple demonstration experiments on a lab scale. Right around the same time frame, Laserzentrum Hanover was also working on active projects, and they have evaluated since 2009 pure magnesium, WE43, and Mag calcium work. And over the years, they have published a few papers, and at least in the case of LZH, the work was done on a commercial machine, which was an SLM solutions machine, and that machine was specially configured to be able to address some of the safety aspects that were considered by LZH and SLM solutions back then, and the work that was reported was therefore that was actually developed on the system here. And again, the focus there was biomedical scaffolds, 5 millimeter by 5 millimeter by 5 millimeter, and then they went on to make simple demonstrator parts. Just a few years after that, Fraunhofer ILT also was, they were active in that area, and their efforts were focused much on a lab scale and on a couple of alloys, AZ91 and WE43, and they were able to very clearly demonstrate vis-a-vis optimization of parameters that you could achieve pretty high densities, which was really exciting to see. The work that resulted in and not only some good density measurements and parameter optimization, but also the ability to get high density. And since then, they've also demonstrated work which has shown some mechanical properties, which I will talk about later on in my presentation. Then some work came out of China from Huzhong University in 2014 timeframe. And this was really the first work with AZ91D that specifically talked about mechanical properties. Again, done on a lab scale, but nevertheless, right around this timeframe, you start to see some of the mechanical properties being discussed and presented. Our effort in this area basically was in the 2015 to 2017 timeframe. We funded some activity with our WE43 powders, and we goes by the trade name MAP43 at a couple of different groups. One was to, so the objective was very simple. We were trying to make powders, and we wanted to work closely to optimize the powders for additive manufacturing applications. So we chose a couple of partners, and it was LZH, and then we worked with ARL Penn State on selective laser melting and on directed energy deposition work. And out of that work basically came mechanical properties that were demonstrated. And again, I have slides that I'll mention about that work. And again, the work out of Beijing Institute was the first work on wire arc additive manufacturing, which is something that Stefan will speak to. And then what we've really seen in the last couple of years has been several groups working on various aspects of magnesium additive. More recently, there was work that came out of Netherlands on solvent-based processes, but we also start to see in the last couple of years work on binder-based processes with magnesium. So these are all promising and basically point to a general increase in the level of activity associated with additive manufacturing of magnesium. So moving on to magnesium alloy production, you're very well positioned in terms of having a combination of small scale capability and full scale capability, and this is over and above what we have in place for pure magnesium. So for a small scale capability, we can make batch sizes between 50 and 60 kilograms. It is a gas atomizer, which is set up so that you can switch between alloys and you can clean it and therefore be able to conduct development and small scale production of various alloys. And this is then supported at the back end with full scale atomization capabilities, which is specifically for magnesium alloy powders. And we have capabilities up to 1.5 tons in terms of batch sizes that we can produce at any point in time. As far as screening and size classification goes, we can go down to 20 microns, and a lot of effort has been put on developing production scale capabilities that allow us now to be able to produce powders in the 20 to 45 micron, 20 to 63 micron range, and any combinations that we can accommodate based on what is necessary for that application. And realizing that custom packaging is important, we work with both small and large scale users, realizing that some of the quantity requirements at this stage of the program may be small. So we can go down to a few kilograms to larger quantities if needed. And we've made and commercially available a list of table on the right. There's several alloys that we have produced, and these are available as standard alloys. Such as the rare earth containing alloys WE43, EV31, Z41, along with magnesium calcium, magnesium aluminum, and several custom alloys that we have atomized over the years. So just one slide for those of you who probably do not have a clear understanding of what a typical powder producer's challenge is. So in an ideal scenario, you would be looking at powders that you produce and be able to find a home for all the powder that you can produce as a part of a run. So in any atomizer run or any ways you're looking at producing powder, you have a distribution that you make. So in an ideal case, you would have the mature applications on the fine powder application side, for example, metal injection molding that uses sub 20 micron powder. And then you would have a proven market for your coarser powder, for example, such as used in traditional PM, and then applications such as thermal spray, etc. One of the things I just wanted to point out is for additive manufacturing, specifically with magnesium alloy powders, you're really looking at a very, very small range for now. And as markets continue to be developed for the finer powders and the coarser powder, that will basically set up the industry to address some of the requirements for larger scale production, because you need to be able to balance out production. Right now, the pricing tends to be a little bit high only because of the fact that the powders we are making are only a small percentage of the powders we produce are going for these applications, and we are continuously looking to develop markets for the broader distribution that is produced as a part of any production run that we do. So in terms of the powders available, we have, this is one of the most common powders that we sell, the electron map 43 powders. It shows the spherical particle size and the key characteristics. These have been well demonstrated to flow very well on powder bed machines, the 20 to 63 micron powder. And again, like I said, custom cuts are available. And these have been well proven to perform well with a combination of high density and good mechanical properties. Same thing with the AZ91, which is another common alloy that we make. Again, we have good feedback from the end users of this powder who have used it for several applications, even outside of additive manufacturing. Now, one of the key things to keep in mind is when you start with an atomized powder, in this case with these alloys. I've shown you examples of AZ91, WE43, and EV31. One of the advantages you have is you're starting with essentially a really miniature casting with very, very fine scale microstructure. And the groups that have worked with these alloys in additive manufacturing go on to report properties which seem to be very promising, but it all starts from having the fine scale structure in the powder. So this is an example of powders all in the 90 micrometer diameter range, which showed dendritic arm spacing of around 2 micrometers. But you can well imagine if you were to go down to mean particle sizes of about 30 to 35 microns, which is what is used in additive manufacturing, you're looking at very, very fine scale grain sizes of the order of maybe less than a micron to around a micron, which gives you a really, really good starting point to be able to preserve the grain structure in your process and therefore achieve significant property enhancement over what you can normally achieve, say, by casting, for example. So looking at some of the aspects to consider for magnesium additive, you're looking at material characteristics. Magnesium melts at 650. However, it has a high vapor pressure, which basically presents some challenges because you're really melting the magnesium powder in these processes. So you've got to be able to address how you're going to adjust the gas flow and account for the magnesium evaporation or the vaporization that's taking place. There is emerging knowledge base, which is evidenced by the large body of data which is being published. One of the key areas to understand would be the safety characteristics of the powders, and these are available from us as well for a couple of alloys which talk about the parameters for explosion severity, minimum ignition energy, limiting oxygen concentration, etc., which would then be valuable to an end user, especially if you're going to be using this to develop your internal handling and safety protocols. Also to keep in mind is whether you need to have specific equipment designed for additive manufacturing, and whether the standard equipments that are being used really need modification. This is an area where you would have to consult with the OEMs to figure out if special changes to the machine are really necessary. And one of the key things that you would want to focus on would be to engage and look at understand the supply chain aspects of who are you buying your powder from. It is clear that even in most basic applications, powders from different manufacturers is often not identical. But when you're looking at a key application like this, you want to make sure that you are having those conversations early on in terms of who are you going to be buying your powders from, and what does the supply chain look like for the powders that you are considering for your application. We did a couple of investigations, as I said, and I'll just briefly cover those with you. On powderbed fusion, this was the work that we had funded with the WE43 alloy powder and also the MAP91. But along with our investigations, several other investigations, which have also focused on WE43, have been able to successfully achieve densities greater than 99.9% with some properties, which I will show you in the next couple of slides. The key observations, however, are that you do have to address the vaporization, the smoke generation that takes place. You've got to address the gas flow optimization. And then, of course, from a safety standpoint, you've got to understand how to handle it during and then after processing. Here is a video that will show you what a powderbed fusion process for magnesium MAP AZ91 powder. So one of the things you see there is the smoke generation, which is very, very common for magnesium. And this is really the area that people most report, and in terms of addressing or being able to address the parameter optimization, that's really where most of the focus tends to be on in terms of reporting the the laser power, the scan speed, and the hatch spacing, etc., to be able to achieve the high densities that you need. In terms of demonstrator parts, this kind of goes on to show what has been done in the last few years. You do see smaller demonstrator parts, as I've shown on the top right, the top bottom, bespoke implants which are being considered. On the left, we see pictures of a large demonstrator part that we built recently, where the original part is a casting. The design incorporated laser powder bed fusion process capabilities. The part weighs 72 grams, which is quite impressive. And when you hold the size, when you hold the part in your hand, it's kind of amazing how light it is, with a height of 9.4 centimeters and a width of 5 centimeters. So there are these demonstrator parts being built, which goes on to show the confidence with magnesium additive, at least with which resides with a few groups right now. On the directed energy deposition side, we were looking at the ability to potentially conduct free-form fabrication using WE-43 powders. And the picture on the right shows the kind of parts that we were able to make. Now, these were simple coupons, but they were about 12 to 15 centimeters long by about 6 centimeters high, which allowed us to pull tensile bars in horizontal and vertical directions and be able to demonstrate at least what a potential feasibility of that process would look like. But again, there are challenges which have to be overcome, which has to do with not only the vaporization and condensation of magnesium, but also the powder suspension that you see when you're trying to feed the powder through a nozzle. So just to give you a sense for where the effort has led to, I have listed AZ91 and WE-43, and I've pulled this information from public domain, including some of our own data, and some of that is unpublished, but it goes on to show you the promising potential for magnesium. So for example, in AZ91, you look at a typical die cast property of 160 in yield and 230 in UTS, and your laser powder bed fusion processes have been able to clearly achieve much significantly better results with respect to the yield and the UTS. And it doesn't take into account different groups working with different powders, different machine setups, and so forth. But the trend is clear that if you get your process parameters right, you are basically capturing the advantage of very fine scale microstructure that you can obtain. Same thing with the WE-43, which is one of the most investigated alloys. And when you look at your cast T6 typical of 180 and 250 with an elongation of 6%, clearly, I mean, some of the best results seem to show that you can even achieve extruded properties, such as reported by Jor et al. from Fraunhofer. And then some of the own work that we have done, we've clearly demonstrated that you can get the yields close to about 200 megapascals with UTS, in some cases exceeding 300 megapascals. And then there's also been some properties reported with AZ91 with a wire arc process. And I'm sure Stefan is going to be speaking about this in the next talk. So clearly, yeah, there is promising initial results, and we expect to be able to hopefully capitalize on this for at least some of the emerging applications. In summary, what I would like to mention is, we have been encouraged by what we see in the industry, and we are on the front end in terms of seeing which groups are working on which applications, and we do see a continued expansion of interest. Several of these powders are commercially available from Luxfer Magtech, and really encouraging to see the mechanical properties that have been demonstrated so far, and these will be the catalysts for basically end users to capture the advantages offered with the design flexibility for additive manufacturing. So with that, I would like to thank you, and I know I've run over my time, but if you have any questions and answers, I could take that later on, perhaps after the other people have completed their presentations.
Thank you. Yes. In matter of time, we had the program designed for 3 speakers, but we took on 4 speakers, so we have to finish that somehow until 3:30. So in that, please, if possible, you can also type the answer in the Q&A. There are 2 questions in the Q&A, or answer to that in the common Q&A later. I would just hang over to the second speaker, which is Stefan Kneigner. He will speak about the process and alloy development for additive manufacturing of magnesium. Stefan received his Master of Science in Engineering from the University of Applied Science in Upper Austria in 2014. And after finishing the university, he started to work for the LKR Ranshofen as a scientist in the premium light metal alloys group. Please, Stefan, we look forward to your presentation.
Yeah, then thank you for your kind introduction and welcome to my presentation about the process and alloy development for additive manufacturing of magnesium. So I've split my presentation into 3 main parts, starting with an overview of the additive manufacturing processes of magnesium. Then the second part is the wire additive manufacturing. That's the process we are focusing on. And the final part is I will show you about projects at LKR, what we are doing at the moment. So here you can see a comparison of additive manufacturing technologies for metals. You have here on this axis the resolution or the part complexity, and you have here the part size. So as you can see, the wire direct energy deposition, you can produce rather large parts, so ranging from 100 centimeters a meter and longer. But the sample geometry or the complexity of the parts is rather low. In comparison, you have the powder processes. So with the powder processes, they allow much higher resolutions and part geometries, complexities, but the part size is limited by the building space. So in the next slides, I will show an overview of the single processes. I will keep this short, as maybe some of you already know this, but I will start with the selective laser melting or the laser powder bed fusion. So a powder deposition method where a high power laser melts the powder in the fabrication chamber, where the part is then produced. So this is in an enclosed chamber with a controlled gas atmosphere. And with this process, you can build parts with a high complexity, with very small structures, so lightweight parts are possible. This process is usable for all magnesium alloys, and net shape or near net shape parts can be produced. Disadvantage is that the powder cannot be fully reused, and the size of the parts is limited by the chamber size. So here are 2 examples for magnesium parts produced via the selective laser melting. We have already seen some. So here are 2 more. As you can see, that small parts with a very high complexity, with hollow areas, and very, very small. So these bridges have a width of lower than 500 microns. As you can see, with post-processing, you can even increase the surface quality of the parts. So small, lightweight, high complex parts. Next process I want to show you is the binder jetting process, or solvent jetting is another name for it. It's again a powder-based method where I can, so here a binder is printed with a printing head onto the powder bed, producing the parts. So again, high parts complexity can be achieved. Small and very light structures possible. And again, like in selective laser melting, net shape or near net shape parts can be produced. Yeah, disadvantage is so a sintering or a binder removal process after the printing process is necessary. And this, especially for magnesium, leads to high porosity and low mechanical properties. So typically in selective laser melting, the properties are higher than for the binder jetting process. And the size of the parts is again limited by the chamber size. So now I come to the wire-based additive manufacturing process. So the process we are focusing on, as you can see here in this schematic representation, wire is molten by an arc, maybe an arc welding torch, but it can be also a laser, it can be an electric arc. So several types are possible here. So this is the wire and arc additive manufacturing process where the wire is molten with an arc welding torch. And then small droplets of the melt are deposited on the substrate to generate a wall or a part. So for wire arc additive manufacturing, standard welding equipment can be used, and you can achieve very high deposition rates with nearly unlimited space. So the space is only limited by the range of the handling device. The process is very material efficient, especially when compared to subtractive methods like milling, because you use almost the whole material coming from the wire. Again, you have some disadvantages. For example, as already said, the part complexity is limited. It depends on the wire diameter, but overall the complexity is limited. And you are also limited, have a limited ability to produce thin walls. And for achieving the best results, the lightest weight, the post-processing machining of the parts is necessary. Yeah, so the building space is limited by the handling device only, and deposition rates for magnesium can be up to 1 kilogram per hour, and in the meanwhile above this. So as this process is capable of high production rates, the aim for process development is also to increase these deposition rates. Yeah, and the layer dimension or the precision is dependent on the wire diameter. So it's typically about 5 times the wire diameter you use. So from 2 to 5 times. So 3 millimeter can be achievable with a 1.2 or even a 1.6 millimeter diameter wire. I will show you a short video of the cold metal transfer process. So as you can see, the wire is touching the part surface and the short circuit is formed. After this, the wire is pulled away from the part surface and you have this electric arc. And this high energy arc melts the wire on the tip. And by the forward movement, this molten droplet is placed on the part. Yeah, so it's layer by layer and small droplets. Here you can see 2 examples of parts produced with the wire additive manufacturing. On the left-hand side, it's an aluminum part, but I use this to show you one side is the milled surface where you have already the finished part. And on the back side, this is still the as fabricated state, how you receive it from the wire arc additive manufacturing process. You can also see that the surface quality is quite good. And here you have additional material which has to be milled away for the final geometry. And on the right-hand side, you can see an example of a rotary part. So the diameter of this is about 30 centimeters. Yeah, we at LKR, we use so only Fronius power sources, namely the CMT Advanced, the CMT Twin, the Magic Wave 5000, Arctic and plasma sources. We have a robot handling system with a maximum load of 45 kilograms. Here you can see the robot and the welding torch, and a workpiece positioner. And in the next month, we are planning to increase our lab size with an additional power source and an additional robot. So now I already come to the projects we are working on currently. So the first project is the wire manufacturing via extrusion pressing. So for the materials development, it is necessary to obtain small amounts of wires in a rather flexible way. So therefore, we have established a processing route for manufacturing welding or filler wires with the extrusion pressing. So the diameters we are capable of manufacture are ranging from 0.8 to 6 millimeters, and the batch size is from 0 to 30 kilograms. So which is completely suitable for our needs for the research and development, especially for welding and this wire additive manufacturing. Larger batch sizes can be produced with industrial collaboration, also using tailor-made alloys. Here you can see the single coil on the roller table of the extrusion press and a single wire coil. So we produce this directly on the coils with an automatic coiling system, so that the material can be subsequently used in processing. Here you can see some wire sections and residue of the extrusion pressing process. Here from a 20 millimeter container in the extrusion press, but we can also use larger scales for longer wires. And on this picture, you can see the surface quality of extruded wire. So here the extruded wire with a diameter of 1.2 millimeters. And here you can see a commercial drawn wire with a diameter of 1.6 millimeters. So the surface quality is comparable in both cases. Yeah, for understanding the process and the material behavior, we started with commercial available filler wires, and so in this case it was AZ61 alloy, and we processed it via the cold metal transfer process you have already seen. And samples, which you can see here, with a dimension of 180 times 30 times 80 millimeters were produced. So for obtaining specimen, and the wall thickness was 5 millimeters. In this case, using this 1.6 millimeter wire, we had a surface roughness for about 0.3 millimeters. Yeah, and we investigated the materials properties in the vertical and also in the horizontal direction. So this is the welding direction. Here in this table, you can see the mechanical properties from tensile test at room temperature. L, so the first number always states the longitudinal, so the welding direction, and the T is the transversal, so the perpendicular to welding direction values. And yeah, they are quite comparable to what we have seen in the presentation before. We have good tensile strength and good fracture strain, and also everything is very comparable in both directions. Also, the grain structures are very comparable. So in the fusion zone and also in the intralayer zone. So this is the fusion zone is the layer exactly between two single layers. So the zone between two layers, and the intralayer zone is in the middle of one layer. So in both cases, they are quite comparable, and we have an average grain diameter of about 27 to 30 microns. We also looked at the chemical composition and compared the chemical composition of the wire with the additive manufactured part. to see if we lose some magnesium due to evaporation. But we have seen that the chemical composition is quite the same. We have a bit higher magnesium values and a bit lower aluminum values in the deposit. So no magnesium is lost. After the commercial wire, we started working with our in-house produced wires, in this case, a magnesium aluminum alloy with additions of calcium and rare earth. Again, the cold metal transfer process was used to produce walls like this, with a wall thickness of 5 millimeters and a layer thickness of 2.5 millimeters. So the deposition rate was higher here, so we also have a higher surface roughness. And here you can see the microstructure in the as fabricated state on the left-hand side and in the aged state. So this was used to show the potential of heat treatments for additive manufactured parts, and also to evaluate the appearance of porosity, something like this. Here you have these tensile test curves compared to the AZ61 we have seen before. And for example, this red line is this in-house produced wire in the T6, so peak aged state. We are almost at 300 megapascals ultimate tensile strength. So with this project, it could be shown that the wire manufacturing route is successful and that the resulting properties can be increased when using special alloys. Yeah, another project I want to show you is the so-called REMAP project, where the focus is on materials development and additive manufacturing processes. So both the powder processes using laser powder bed fusion and also, again, the wire arc additive manufacturing. So we use both processes for comparison, and we produce the powders and the wires in-house in order to establish the whole processing route for investigations within the project team. In this picture, you can see the lab atomizer used at the partner, the Technical University in Brünn, and the first batch of magnesium powder with an particle size ranging from 32 to 88 microns and the mean size of 56 microns. So, and at the moment we are experimenting with twin cold metal transfer for increased deposition rates. So in this process, 2 electrodes are used at the same time within one welding torch. So this allows to increase the deposition rates, and in future, maybe it can also be used for in situ alloying when 2 different wires or 2 wires with different chemical compositions are used at the same time. So here again, the deposition sequence now using double wires. Can also see from the video that the wall thickness is increased. So in fact, you can double the deposition rate. Yeah, so finally, I want to thank the funding organizations for supporting the projects. And I also want to thank you for your attention. Thank you.
Thank you, Stefan. It was a very interesting presentation. I think one of the questions, is it an alloy or pure for the wire additive manufacturing, was answered during the presentation.
Mm-hmm. Yeah, so it was an alloy.
Yeah, and there's another question about the gas protection, very important for magnesium.
Yes, so the gas protection, we use a gas mixture of 70% argon and 30% helium. And it is included in the welding torch we use. So we have this gas protection directly from the torch.
Okay, I see no further questions at the moment. Yeah, there's one more. Is it possible to increase the detail of the user using a thinner wire?
Yes, it is possible. So the smallest wire we produce is the 0.8 millimeter wire. You can reduce the wall thickness to about 2 millimeters at the moment, but rather confident and that with smaller diameter wires and with adapted processing parameters, so maybe lower energy input, you can decrease the wall thickness even further. But you will not reach the complexity or the small size of powder produced additive manufacturing processes.
Okay, thank you. The Q&A session stays open, so for every speaker who has already had his term. I would call to the screen our next speaker. It's Dr. Thomas Ebel, and his talk will be about sintering-based additive manufacturing of magnesium alloys, motivation, and today's status. Thomas is head of department at the Helmholtz Zentrum Geestach. We focus on powder metallurgical techniques for processing of titanium and magnesium. Thomas, please.
Thank you very much, Martin, and hello to the audience. Yeah, I will talk about sintering, and to be more precise, I will talk about binder-based sintering. We heard about binder jetting. That's a little bit different to that I will talk about, because what I mean is that we really mix before the shaping process the metal powder with a polymeric binder, so we can get a feedstock like granules or also like filaments or like a slurry or whatever you want. And this feedstock then can be processed by different shaping technologies. Today, there's really a number of different techniques, and this list is still increasing. We are using in our institute mainly the first three techniques, and there's fused filament fabrication, which uses filaments, of course, composite extrusion modeling, which uses granules, and these granules are the same we are also using for injection molding. Independent of the technology you use now for shaping, you need, after the shaping process, a debinding step. So that means you remove the binder. Usually it's a two-step process, one solvent debinding and then a thermal debinding prior to sintering. And after sintering, you have really the part which is ready to use. One really benefit of this processing is that the binder protects the powder. So this feedstock is, you can really handle very easily. It's a safe handling you get. And the advantage we see in the sintering process is that the material gets a really very homogeneous heating and cooling. So the entire part gets really the same heat treatment, which results in an absolutely homogeneous microstructure, isotropic mechanical properties, and no stress after the sintering. Furthermore, what is really very nice is that the microstructure itself is independent of geometry. So it really doesn't matter if you process a small part with a thin wall or a thicker wall, you always get the same microstructure. Oh, sorry. Sintering itself is in principle a very simple process. So you have the powder, you heat it up, and you will observe that in the early stages, sintering necks are formed, and these necks grow. And after a while, usually several hours, you get a nearly dense material. You have some small isolated pores, but the rest is really a homogeneous material, and you cannot recognize the original powder particles. So it's really well, a new material, so to say. That sounds simple, but the problem is is always, in the case of metals at least, especially this first process relies on the cleanliness of the surface. And on metals, you have usually an oxide layer, and this oxide layer can hinder sintering. And to be honest, what these images here, they are titanium. And in the case of titanium, it is quite nice because the oxide layer, which is in principle a very stable one, it dissolves at temperatures above 400 degrees. And then the oxygen is just diffusing into the powder particles, and the surface itself is pure metallic. So it's very nicely sinterable. Titanium works really nice. In the case of magnesium, it's a little bit different. You have, again, an oxide layer, but this oxide layer is stable until melting of the material. And this oxide layer really hinders the sintering. But there are some tricks. For example, you can provide a little bit of liquid phase. You can do it by sintering in the two-phase field of an alloy, or you mix different alloys. One is melting a little bit earlier, and this melt then can break up the oxide, and then you get metallic contact between the particles, and the powder particles can sinter, but these oxide particles remain in the material. It's in principle, it is even a little bit more complicated, because this whole sintering process takes place in a furnace, and the furnace has not a really clean atmosphere. You have oxygen and you have carbon from the binder, and so on and so on. And the trick is really to avoid this these elements again pollute the surface, and that's really a little bit tricky and it needs a little bit experience. Nevertheless, if you have this experience, then the powder can sinter very nicely, and you see here the pictures which are quite similar to the titanium ones. There's the one difference, and that's these oxides. As I said before, you can see them in the microstructure, in the material, and you can see it's in principle it's the surface of the former particles. So you could say oxides, that's very bad, but they have at least one benefit, and this is visible here in this picture. This is the same alloy processed by casting, by sintering, so metal injection molding in this case, and extrusion. And you see the big difference in grain size. The nice thing is really that these oxides hinder grain growth very strongly. So in principle, you get the grain size of the powder particles. When you use finer powder particles, you can really also get a little bit finer grain size. Not that fine as in the extruded case, of course, that's really very, very nice, but at least much better than casting. And you can see this in the mechanical properties in a comparison. So the UTS is somewhere between the cast and the extruded material, typically, but this is UTS. If you compare yield strength, you can see that there's nearly no difference between casting and MIM. So the extruded material is simply a very good one. That's no question. We also processed an AZ alloy. It's an AZ81, and we looked also if we can see any influence of this T4 treatment, which is usually applied to these alloys. And again, we compared in this case with cast material from the literature values, and you can again see it's quite similar to the cast material. So I would say the properties are good, but they are not excellent, but they are really sound, and you can use this sintered material, and that's really a metal injection molded material. We compared also between MIM and fused filament fabrication. Again, this 81 alloy, and you can see yield strength is more or less the same. We have a difference in the case of the ultimate tensile stress and also in elongation to fracture. You could think that is because of printing flaws in the case of the fused filament fabrication, but we don't see printing defects. But what we observe is a slightly higher porosity in the case of the additive manufactured parts, and this is probably due to the fact that for the filament we need a little bit smaller powder load. So we need more binder, and that means that the distance between the powder particles at the start of the sintering process is a little bit larger. But at least, well, these are first results, and it's really promising. So it seems that it's also possible to apply fused filament fabrication. That's exactly what we want to do, of course. These are a few parts. First parts, and well, of course, you can optimize the geometry, so that's not a question. But you can see that we have a very homogeneous microstructure here, and we can see it simply works. We are not a part producer. We are looking for the material, but of course you can optimize here. And we also applied our 3D printer, which is using granules, so the composite extrusion modeling, and we made a different part from a different alloy. And you can see that it's, well, again, not really perfect, but it works. And what is really nice, if we make a cross section through the material, and we look if for the fusion zones again. So it means, can we see where the layers were? And these blue lines here mark the previous printing layers, and we can do a little bit higher magnification. We can see now we have really a homogeneous material. So after sintering, we have one material, and we don't see these printing layers. It's, as I said, there's much room for optimization. But in the end, when I like to sum up a little bit, the actual status now. So I would say, first of all, if you sinter magnesium, it always means you have two challenges. And one is really the stable oxide layer. So you have to find a way to break this layer up, because otherwise the powder will usually not sinter. The second challenge is, of course, magnesium is very reactive. So you have to avoid any additional oxygen and if possible also carbon and so on. So that means you need a special furnace for this, and you have really to work very clean. But if you can handle this, you can really get parts with different technologies, which are quite simple. You have a safe handling, and there are some things which are also really beneficial if you compare it with casting at least. So the grain size is really limited. That's very nice. As I said, you can apply different shaping techniques. The mechanical properties seems to be somewhere between cast and extruded material. So you will probably not get the best properties, but you will get sound properties. Of course, this is a very early stage in principle, So the research topics we are working on now are to understand the dependence of the sintering on alloy composition, because what we observe is that we have some alloys which sinter very nicely, others are a little bit different. So in many cases we have really alloys with a porosity after sintering between 1% and 2%. That's really low. So it is sintering, but it depends on the process and on the alloy. Then we like to develop a robust process, or also a robust alloy, which is more tolerant against variations of the sintering process. And what we of course also see for the specific shaping technique, we need dedicated binders. So we are also doing binder development and use binder components which do not react with the magnesium in such a way that they hinder sintering. At this point, I like to end and say a big thank you to my colleagues Martin Wolf, Henrik Burisch, and Johannes Schaper. They actually did this work. I was only reporting, and thank you very much for your attention.
Thank you, Thomas. I see the question and answer session is really working, so our questions are answered. I see one question for you from Michael. What are typical dimensions of sintered produced parts?
Typically, at least in the case if you use binder based techniques, because you usually want to make rather small parts. So it means typically you have something like a few centimeters. And because you have to remove the binder, it means that the wall thickness shouldn't be too large. So let's say it is, let's say maximum 5 to 10 millimeters, if possible. It depends on the exact part, but you are usually speaking about more smaller parts, and sintering means always that the part is shrinking also, and these are things you have to consider.
Okay, thank you. There are a couple of more questions. Please, Thomas, see if you could answer them perhaps via the chat section. And I would want to welcome our last speaker for the webinar, and it's Marco Salvisberg. And Marco will talk about advantages of additive manufacturing and successful application of the additive manufacturing demonstrated on basis of real customer projects. Marco. Okay, I think it's taking longer than expected. Can I please ask the other presenters to unmute their mics and probably their cameras, and we can go into a broader Q&A. Okay, I see Thomas is on. I don't know if there are any questions left. You answered already, but if you could elaborate on some questions live, that would be appreciated. I see, Raj, if you answered a few questions online, do you also want to point out one or two questions in the session?
There's been one that just came across. Hang on. Sure. I mean, do you want me to?
Yes, please.
Martin.
We are still waiting on Marco. I don't know if he's he's making it back. So we're going to use the time to answer some questions.
Okay, do you want to just, so am I live now?
Yes, you are.
Okay. So there was a question on, the question was, when you look at the literature, you see the researchers have achieved part densities greater than 99.5% for a wide range of energy densities. The question is asking, do you know if there is any powder characteristics factors for this? So the best way to think about this is when customers come to us, they usually have they usually know what alloy and what particle size they would want for a specific additive applications, and it usually is within the realm of 20 to 45, 20 to 63 microns in that range, and they know what alloys they need. Sometimes they don't, so we will recommend what alloys they need. But clearly, from that point on, the ability to actually process the powder is fundamentally going to be tied into what knowledge base do they have. I mean, we come across all different kinds of customers, some who have, have some experience with magnesium before, so they know where to start, but some who are starting for the first time, they may not have used powders from other suppliers. So all these questions become important. And is there a powder characteristic factors that can lead to a greater density? The answer is going to be based on what kind of process knowledge do you have, what kind of machine do you have, and how are you basically able to handle the powder and take the precaution, and basically the ability of the group to have the knowledge base to get to those density levels. The machines are different. The way you operate the machines, there are nuances, so it's really difficult to say. But I can tell you one thing: it will ultimately all be tied into the quality of the powder. I cannot re-emphasize that point. I mean, there are powders from different suppliers, and for a sensitive process like additive manufacturing, you will probably find a difference. The challenge is therefore to really identify, is it the powder, or is it basically how you have used the powder and use the process to achieve whatever you're trying to achieve, whether it's the density or whether it's the right microstructure. So it's a really difficult question to answer, but it really goes back to the groups who are working with any supplier's powder to give the feedback to the group and work with them on successive iterations if that is the objective of the program. So that's the best way I can answer that question.
Thank you. Stefan, can you elaborate on some questions you got and you would like to discuss as well?
So I have one question from Ellen Luo about the lab atomizer and how much powder do you produce at a time? So at the moment we started in February this year with the first atomizing of the powders. So we are not yet in a full production or anything like this. So we produced the first batch with around 50 grams at the moment, only for characterization. But what I have learned from steel, we are able to make about 200 grams per hour. So yeah, it's a lab scale. But for the research, it's sufficient, I would say.
Thank you. Thomas, you want to keep some of your questions live?
Yes, there was a very important question also about the liquid fraction we have during sintering, because that's exactly the central point, I would say. It is very important how much liquid we get, and especially also the wetting of the powder by the liquid. And this is something where in the moment we really have only ideas. It is very, very hard to observe this. What we know is that the liquid fraction we need depends very strongly on the alloy itself. That is important. what we also see is sometimes that sometimes we just press powders and sinter them without binder, and we have alloys where we can see sintering is very hard in this case. When we add binder, it works very, very nicely. So what happens on the surface during sintering? That's very, very important to understand the whole process. And here we are really, well, in a very early stage. And but actually we are just now running a PhD thesis also exactly about this liquid phase problem. So I would say in that moment, when we understand what really happens on the surface, then we will be able really to sinter all alloys very nicely. And it's possible also that was also a question, that it's then really necessary to adapt the binder exactly to the composition of the alloy. So these are things are issues we are thinking of, but it's future work. In the moment, I cannot answer it. That's my problem.
Thank you very much, Thomas. Yeah, we have the opposite problem. Normally you run out of time. Today we have the luxury to have time enough, but I think everybody is busy. But I see that Marco is rejoining, so we have 10 minutes. So I will give him the floor for 10 minutes after. Before rounding up, to see if he is successful to present at least some of his presentation. I think we're confronted with technical issues today, but that's yeah, I think you get used to that. It's also a very data traffic time of the day, I think.
So maybe in the meantime, there's one more question I can answer. So did you perform some other characterizations such as corrosion or fire resistance? I'm not sure for whom this question is, but I can answer it as, since via additive manufacturing in our project, we are mostly focused on aerospace applications. So definitely we have corrosion characterizations, and we also tested the fire resistance. This is also one reason why I had in my presentation this calcium and yttrium alloyed magnesium alloy. So there is something here, and we have results, and I can share them. If you maybe send me an email, I can share the results with you.
Thank you, Stefan. I see that some of the participants have already asked the presenters for email addresses, and those have been exchanged already. We'll try to, when we follow up with the webinar, you will get the email addresses of the presenters as well, and you also can connect them via the IMA as well. I'm afraid that we're not getting Marco back on, because he was short and then he's lost again. So I think he has problems with his internet connection, and I think we are running out of time for him anyway. I saw that it was a very active Q&A, so I think that's the backbone of our webinar, combined with very interesting presentations. And this we had today. Thank you very much for all the speakers. Thank you for participating on the webinar. We have almost reached 100 participants, which is not a record, but very appreciated by the IMA as well. just want to make some advertisement at the end. The IMA is a very active global network, and we have a European and an Americas committee where you as an individual or company can be an active part on that. So if you are interested, visit our website or send me an email. I can certainly invite you to as a guest to one of our committee meetings. And normally we have, or we are running a worldwide conference every year. Last year it was an online edition, and this year it was not decided yet, but it is scheduled for the 25th and to 27th of August. And the call for papers is still open. I think it was prolonged as well. So if you have an interesting presentation topic around magnesium, please send in a paper. The same goes for awards. We have a nicely appreciated yearly awards program in different categories. So if you have a nice part or running a nice process, please let us know as well. This year is new, a health and safety award, where we are looking for innovative, easy, but very effectful actions and prevention in terms of safety questions for magnesium. This is open not only to members, the awards and the presentations are of course open to everybody. So with this, I thank you again for the speakers. I hope to see you at one of our next events, and the audience as well. I hope to see you and as well at our conference and in one of our next webinars. I hope you find it interesting, and we keep following up. Thank you very much, and have a good remaining day. Thank you. Bye-bye.
Thank you all. Bye.
Thank you. Bye.
A warm welcome also from my side. In the next 15 to 20 minutes, I will show you some of our activities in the field of additive manufacturing and present current projects using real customer examples. I would like to make one thing clear from the start. The examples and applications I'm going to present today will not be magnesium, as we as a technology user are dependent on obtaining the appropriate equipment from our suppliers. And these suppliers are not yet at the stage in which standard machines for processing magnesium can be used. Nevertheless, you will see how business models and processes will have to adapt as this new technologies offers many opportunities to our customers. GF is divided into 3 strong divisions. 2 of those invest heavily in additive manufacturing. On one hand, we have GF Machining Solutions, which produce milling and wire EDM machines, and for some years now also 3D printers. And on the other hand, we have GF Casting Solutions, where we manufacture components according to the customer requirements using various production processes. As most of you are probably aware, we produce components by means of high-pressure die casting in aluminium and magnesium, and sand casting in iron. But due to a strategic acquisition, we have also entered into the precision casting and additive manufacturing field. These activities are combined in the business unit Precision Casting and Additive Manufacturing. But why did we, as a precision casting foundry, start with additive manufacturing more than 5 years ago? The answer is quite simple: because of our customers. Our customers approached us in the past and made us aware of the fact that some components that we are currently casting will most likely be manufactured using additive manufacturing in the future. This is for the simple reason that the traditional manufacturing process can only produce the new and even more extreme designs with great difficulty, or not even at all. However, in order to further increase the efficiency of the engines and the turbines of our customers, exactly these extreme designs are needed. Today, we have the ability to respond to our customer needs with the right technology, and regardless of whether a component is printed or cast, the so-called post-processes such as heat treatment or non-destructive testing or special surface treatments can be applied in the same qualified production location. In the AM Motion Center Stabio in southern Switzerland, our main location for additive manufacturing, we offer all the necessary process steps along the whole value chain. It all starts with consulting and training. In this first step, we help customers find the right application for 3D printing. Once we have found the right application, we support the customers in optimizing the design or even design parts from scratch. Once we have printable geometry, we can produce in a few weeks or even some days first functional prototypes for our end customers. Sometimes we can even produce final use parts within some days. We have adapted our quality system, which is EN 9100 certified, in order to deal with the very fast-paced AM technology in terms of quality and qualification. Once a process has been qualified and all parameters have been frozen, we can serial produce components with a consistently high quality. To my components are usually not ready for use after printing, as we saw also in the previous presentation. To make the life of our customers as easy as possible, we supply parts ready to mount as we apply all the necessary processes in-house. But now to the promised application cases. I'm very happy to be able to present you two real examples. As you can imagine, our customers are very restrictive when it comes to sharing information for these critical components. Here is the first application from aviation. This customer actually wanted to produce a new front frame using precision casting. But however, we quickly found out that the time frame he had in mind and which he needed the first components was simply not possible with the traditional process. So he was asking to get parts within 3 months, but our engineering from the precision casting plant said to produce such a complex part, it would need at least 1 year until you get the part that you can use. So let's have a look at the front frame. As you can see here, the part is quite big. So we are using laser powderbed fusion, and the outer flange has a total diameter of 560, and the diameter of this part here, or even here, is around 490, and the weight is 55 kg, excluding support structure. Material in this case is a nickel-based alloy called Inconel 718. To solve this the problem of this very limited time, we proposed a solution in 3D printing. And most of the time, skepticism arises when we propose new technologies to the customers that are hardly known or not known at all. But in this case, our suggestion fell on open ears, as the customer suddenly had the opportunity to catch up the overall project's delay that he had accumulated so far. And then sometime it happened that we observe, and then something happened that we observe very often. I can still remember this discussion very well. We were sitting in a meeting and the customer explained to us that he would then have to attach various flanges and brackets and would therefore have to test the weldability of the material. So I asked him why we didn't print these features directly, because this generates almost no additional cost, and at the same time it increases the additional value of the component extremely. The customer recognized this advantage, and we were able to increase the functionality of the parts by adding these brackets and flanges without adding much additional cost. In addition, we could add cooling channels that are normally drilled into these components by laser. As you can assume, this is quite a high cost, as there are over 2,000 channels drilled by laser in this part. And we were able to substitute this entire process by inserting these cooling channels directly during the printing process. Again, here without generating any additional cost. So what were the benefits for our customer? On one hand, the lead time reduction. So this project for him was only feasible because we reduced the lead time from well over 12 months to only 12 working weeks. As we were not using any tooling, this cost felt completely apart. So therefore, the overall cost for the development compared with what we have offered for the precision casting side was 85% lower. And even more interesting, having such a complex nickel-based part, even the serial price to produce a part like this would be 20% lower. And as of today, we have done already several design iterations, and the flexibility is quite high because we do not have a tooling. So we are working on the digital twin, means the 3D model. And there is, besides some engineering fees, there is no other cost associated with the part. And in the end, thanks to these new cooling channels and the parts and functions that we could integrate into the component, the performance of the overall part is higher than it was before. Here is another example from the industrial gas turbine field. This client is more advanced and has been using AM as a production process for several years. The task he set us was not less interesting and challenging than with the front frame. The customer wanted us to analyze the combustion chamber for this new gas turbine and produce it 50% cheaper than it's currently possible with current production technologies. Even for me, as a very positive person, this challenge seemed almost impossible to solve at the first place. The previous component was produced using traditional manufacturing technologies such as casting, forging, and sheet metal forming, and finally everything was welded together. To make this clear, we talk about well over 40 different components manufactured with 4 different manufacturing technologies. So here, let's have a look at the part. As you can see, the dimensions using laser powder bed fusion are quite impressive. We have an outer diameter of 500 millimeters, and the set height is 425 millimeters. And also here you see many features and parts integrated into one single piece. Thanks to additive manufacturing, we were able then to combine these 40 parts, as mentioned before, in one single component, reducing overall cost by 50%. And even more importantly, cutting delivery time from over a year to less than 8 weeks. So what were the main benefits that the customer saw? On one hand, the reduction of complexity in the supply chain due to the part integration. So from over 40 different components from different suppliers to one component from one supplier. Then the lead time reduction. Before they had to plan their needs quite well, and now thanks to additive manufacturing, they're able to plan also on short notice and to reduce delivery time in a very important way, down to 8 weeks. And then the part performance. So also here we could integrate other process steps, as for example cooling channels, and the tolerances of the overall part are way tighter than they were before. And furthermore, the machinability of the 3D printed part is way better than it was on the forged, welded, casted assembly. This is thanks to a very fine and homogeneous grain structure that we see on this Hastelloy X part. And then obviously the cost is the total cost of ownership, which is 50% lower for the customer as compared with the previous assembly group. So let me summarize quickly. As you have seen, additive manufacturing can be of great added value. However, in 90% of the cases, you have to develop components from scratch and not simply copy traditional processes. This is how the process can develop its full performance capability. As I said at the beginning of my presentation, we are currently focusing on nickel-based alloys and have now started printing various aluminum alloys. The next family of parts will be titanium, which we are developing for our material portfolio. As soon as there are printers and processes on the market that allow us to process magnesium in a safely and cost-efficient way, we will certainly move also in this direction. Thank you again for your thank you again for your participation, and I want to say sorry for the interruption due to my internet problems. If you have any questions or suggestions, so reach out to me and I will be more than happy to answer them or even set up a brief meeting with you. So thank you again and have a nice evening. Bye-bye.